In this podcast, I'm going to talk about drones. When I was a kid, it was not even imagined that you could actually build something which could actually fly and be controlled. There was remote-controlled aircraft, but the idea of a helicopter that you could control from the ground and could be powered by electricity was just a dream. Now drones seem to be everywhere, and what I'm going to talk about is some of the I suppose the technical uses of drones, or the actual problems of using drones. The unknown cost in using a drone, because it's just electricity, surely there'll be, once you've invested in the drone, there'll be no ongoing cost. But there is a ongoing cost, and it's this is the LiPo battery. It's lithium polymer battery, and as you can see, this one is a little bit bulged. And so these have a lifetime, and if they've got a lifetime, they've got a cost. And there's a trade-off. You can actually charge it up very quickly if you want to use it very enthusiastically, but then it will only last a very short time. So the actual cost, this is a major cost factor, and it's also a weakness factor. You can see here that this has lost a wire. The actual wires come out. I'll have to fix it in, which is a major weakness. Now, it comes out, it comes out a lot of the time simply because you're connecting and reconnecting. There's the connection to the actual drone itself and the connection to the charging thing. So this is one of the things that I want to address that may not be possible in the immediate future, but down the track, the use of supercapacitors to take the edge off, at least a combination of supercapacitors and those lithium polymer batteries. Now they are large, but they're not necessarily as heavy, so it's the energy capacity per gram which is important. And of course supercapacitors, unlike those capacitors, have almost an infinite charge life. So for particular applications where you just want to charge the drone and use it for a few minutes and then come back, a supercapacitor is ideal. Supercapacitors are electrostatic batteries, whereas that's a chemical battery configured to have a very high charge, and it's got a large amount of energy stored in it. A supercapacitor has a large power availability, that is, a large power output, but a large amount of power can be put into it to charge it, so you can charge it in a very quick time. So even though you may not be using all the power available, so it could actually just arc and spark, you can actually, the high power of the supercapacitor means that it can be charged very quickly. So typically a few minutes at 4 amps, or if you actually have a pad which charges up your drone, which is you charge your supercapacitors in a charging pad, and those can provide very high current into your supercapacitors in order to charge your supercapacitors up. So what I'm getting at is that if we can actually use supercapacitors with drones, if we're not going to use them for very long extended periods, or if we want to use them for extended periods, we have a combination of balance between the lithium polymer batteries and the short batteries. So your lithium polymer battery stays up there and is used at a long time cycle, but if you're using it at a number of very short time cycles, the lithium polymer batteries are not clear. And so we have now the point is that you don't get very much advantage if you still have to take your drone up, unplug it, and put in your charging for the drone. So this is sort of the next idea, is with a drone with 6 feet arranged in a hexagon. So there's a 6 propeller drone. Those 6 feet can have charge recepting pads on, and so when the drone lands, those 6, I'll put the 6 down, can actually land. The pads or wires hanging off those pads can land down and hit a charging pad. Now yes, you could actually just get it to go in and actually put in a charging plug, go in and sit in a charging plug. However, you can actually make a large area charging pad And to do this, you have to give away the knowledge of what the polarity of what foot it is. So for each foot, you have wires going through a diode, which means that it will detect the polarity of the foot that lands. So if the foot lands on a positive terminal, that foot will actually go up. The positive diode will go up. If it lands on a negative terminal, the diode's switched around and will go to the negative part of the charging of the supercapacitor actually inside your drone. So we then have the problem that what happens if you've got pads and the pads are sufficiently close together that your foot shorts the pad. So that means that there has to be a gap between your pads equal to the size of the feet. I suppose the other thing is that the width of the pad has to be shorter than the entire drone. So the entire drone can't actually land with some feet in some neutral territory and some feet on one electrode. So the electrode for orientation, so you've got electrode pads roughly half the size of the drone going across, and you want it such that a foot actually has to sit down. There is geometry for which you can do this, but you can have a large meter pad that's similar to this, and the drone just simply has to land on it or hover above it if there are wires hang down from it, and it will charge within a minute or even less. Now, the entire idea is to get over the idea of using electronics or you need electronics to charge it, storing your charge produced by a power supply. So the power supply should supply supercapacitors within your charging pad. And so when the drone lands over the top, it can quickly recharge, so it can land and recharge. So an example of where that would be useful is if you have a lesson with students with a high turnover using the drone for 5 minutes or less to do various things, or drone sports. And of course, if you actually think a long way ahead, you have the sort of very similar to drone combat in terms of you have your long-range fighters coming in, which requires batteries, but you have short-range interceptor drones if they want to intercept. These want to take off quickly, do some intercepting, and then come back. They've got a short interception life if they're local for it. And that's one aspect of drone development which I would be very interested in. Of course, as the capacitor, the energy stored in a capacitor is half CV squared. And the voltage is limited, that you can raise the energy stored in it too. But also the actual voltage on the capacitor drops. So if the capacitor is fully charged at 2.7 volts, it'll be 2.7 volts. By the time it's discharged complete, or 50%, the voltage will be 50%. So you need some management system there at the low voltages to actually mother it in and actually have a lithium polymer battery being able to supply the emergency energy as it comes in. But that tail is a very slow discharge, and you can have slow recharge for that eventuality. So even though it holds a large amount of voltage, a large amount of power and energy to lift your drone up, the actual dissipation goes down, and it's pretty easy to see because the supercapacitor is an electrostatic battery, and so the electrostatic battery involves force over there. Now just to go on to the origin of supercapacitors, they're able to massively increase the surface area inside the supercapacitor, and also reduce the gap, the gap between electrodes or plates in the supercapacitor. So your formula for your capacitance is epsilon naught area of the capacitance divided by the distance of the capacitor, the distance between the plates. And so by using special materials, you can get a massive increase in area by using nano contour surfaces or graphene folded surfaces, but you can also reduce the distance to molecular distance by actually coating it with a electrode, which means that you get an extra surface in between the two capacitors, and then on top of that you can increase the charge storage or energy storage by using something lithium dopium on those charged layers, which can increase the power of it. So it's getting very close towards a lithium polymer battery, but the lithium polymer batteries, as you can see, age. You can actually feel them if they're slightly old. They get a bit puffy. And what actually happens is, as you've got chemicals actually moving within the lithium polymer battery, the chemicals eventually form these things called dendrites, hairs, and actually destroy your battery over time. So there's a limited amount of charging. I think 3,000 or something around that amount. Now, if you are prepared to actually charge it really slowly, you can get almost infinite amount of time. So if you're prepared to charge it over 2 days rather than a couple of hours, you can keep on doing that. And in an education setting, you can have your lesson and then have it charged over a day for the next lesson, or interchange batteries. Now this gets another point of trying to map the energy source in the drone to its actual end use. Now, obviously, if you've got the idea of a TV program or something where you have to have the drone sitting there for the event to happen, and you need the drone to be a long distance away. But say for something where you know when the drone has to be there, the drone can actually go there, photograph, and come back. So say in a race, you can see when someone is coming towards the finishing line at a particular point. You can then send the drone up, photograph, and come back. And so this is trying to actually map the energy characteristics of your energy supply to the task at hand. And so we now have the issue of what is a possible application of a drone which can actually effectively and cheaply go on a very short journey up and a short journey down. That's essentially what you'll get out of it if you start to use supercapacitors. And now what you can do there is have the drone actually carry a drone-to-drone package, so that there's some sort of package underneath on a string, and you can have another long-range drone that is not necessarily the propellers going like this, but the, sort of a plane type drone come past and grab the package, and that's designed. So drones are not necessarily designed to actually travel very quickly over a long distance and navigate down a corridor, although a plane drone may not necessarily be electrically powered. It may be motor powered. There's certain various chemicals you can put into which are quite effective, not necessarily petrol. I can think of other chemicals you can use to power your drone. But the idea of this is, and these drones are not particularly good, so you use the advantage of a drone which can go up and down really quickly. That's its specialty. You can have another drone which can actually travel long distances, and its specialty is traveling long distances. Its specialty is not necessarily going up and down, and so it can pick up the package mid-air, travel along, possibly even deliver it to another, like either drop the package or deliver it to another drone waiting to bring the package down. So you can actually use a combination of specialist drones to deliver a package a long distance very quickly and very, very cheaply, or the economics of it can be much better long term. This is obviously Peter Hill Explains. It's a podcast. The previous podcast, I've had my green screen up. I've got it at the moment up behind me. I'll work on it. And the overall idea is that I get a habit of explaining small things and presenting them and basically improving and sharing and getting some feedback as I go along. Thanks for listening. In the meantime, keep on thinking, doing and teaching science.